Good evening, ladies and gentlemen. I hope it was clear in the advertisement for this talk that the description of the 170-year-old mystery applied to the subject and not the speaker. What I want to do is to tell you a little bit about this multiple star Zeta Cancri that I've looked at quite a bit. But I also want to tell you a little bit about the measurement of stellar radio velocities. Sherman is not quite accurate in saying that I look at variable stars. Well, he is in a sense that the variable stars are usually photometrically variable stars, whereas the ones that I look at, they tend to be stars whose radio velocities vary. The radio velocity being the motion of the star in the line of sight. And the reason that it varies is because the star is going round in some sort of an orbit with another star. Maybe you can see both of them in the spectrum, maybe not. And the fundamental principle which is used for measuring the radio velocities of stars is the Doppler shift. Well, there's one great advantage in measuring radio velocities as opposed to the transverse velocities. You could imagine measuring the motions, thinking of the motions of stars in a spherical polar coordinate system, in which instead of having 3 coordinates at right angles, you've got one radial to yourself, and the other 2 are the crosswise motions. Now, to determine the motion transversely, you've got to take a picture of the star field or measure the direction towards the star now, and then you've got to wait a suitable interval while it actually changes by an appreciable amount and measure it again or take another picture. You can assume maybe that many of the stars are very faint and far away, and you can see the motion of a nearby one against them. But a good interval to wait might be 100 years or something like that, although impatient people have been known to try and do it on a shorter time scale, especially with satellites with HARCOS, which made measurements that were very accurate, and so it could manage with a shorter time scale. But the great advantage of measuring the Doppler shift is that the Doppler shift is rather like a speedometer. It measures the velocity here and now, and you don't have to wait for the star to move. You're actually measuring the derivative of its position, the rate at which it's going, right at the time of observation. So in an observation taking a minute or 5 minutes, you can determine that velocity perfectly unambiguously. Well, I developed on the 36-inch telescope at the observatory here the first instrument that measured the Doppler shift by a process of cross-correlation. And although the, as it were, establishment in the field didn't like the procedure initially and tried to persuade me that it was invalid, after a time they embraced the method themselves. And now nobody would know how to measure the velocity any other way. And in order to explain to you how it came about, I think it is quite sort of interesting physics to see how it is. I shall insult you by starting right at the beginning with explanation of as it were, spectroscopy and what one actually used to do in order to measure velocities before the days of cross-correlation, although spectroscopy still works in just the same way, whether it's cross-correlation or photographic spectroscopy. This very elementary view graph is supposed to show the 3 types of spectrum that there are. If you have a hot opaque light source, it gives a continuous spectrum. You can imagine this as, I was going to say, as just a slice through a rainbow. The rainbow would have to go that way, I think. Anyway, all the colours are present. Whereas the spectrum from a hot gas or a gas which is excited in some way, like electrically, electrically in these lights here, is an emission spectrum, and if it's sodium, it just gives this one yellow line. It's actually double if you look at it in detail. Whereas if you have a continuous spectrum which comes from this hot source that passes through a cloud of sodium vapor, the sodium, as well as being able to emit this characteristic line, it can absorb it if it comes from a hotter source. And so you get a spectrum which has all the other colours, but the yellow, which corresponds to the sodium, is missing. And so this is called an absorption spectrum, which has dark line in it, and all the chemical elements have their own specific absorption lines. So now this is the principle of the spectrograph. That you have the star, which serves as an opaque source, and its atmosphere absorbs it's a cooler gas in front of the opaque source, and so it absorbs some of the lines of the various chemical elements in the atmosphere, and it goes into our telescope, and it goes to a spectrograph. And meanwhile, if you were an old-fashioned observer with photographic plates, you've got a laboratory source, and you know the velocity of the laboratory source because it's at rest with respect to you. And it was typically an arc that was struck between iron electrodes, and iron happens to give a very rich spectrum, which was a help. And that goes to the spectrograph too. The spectrograph was arranged so that you've got the spectrum of the iron arc on either side of the star spectrum. So you've got a spectrum that looked like this, and it was photographed on a photographic plate, in which this is supposed to be the spectrum in the violet, because it's violet because, of course, you only use black and white photographic plates, but they're most sensitive in the violet part of the spectrum, and that was the part that people normally looked at. Nowadays it happens that the detectors are most sensitive in the red, and so people work in the red, but it's not from choice, it's because it's easiest to do. And that was why people always used to work in the violet. So you've got this spectrum of the iron arc here and here, and between the two you've got the star spectrum. And I've drawn this in a bit of an idealized way so that it looks as if the star only has these dark absorption lines in places that correspond to the emission lines. But to our first approximation, that is what a star spectrum, at any rate of some sorts of stars, looks like. It does have a lot of lines which arise from iron. And you can see I've drawn this so that all the absorption lines appear to be displaced a bit from the corresponding emission lines. And that displacement, which I've indicated here, is the Doppler shift. And the sign and amount of the displacement tells you the sign and amount of the velocity of the star with respect to yourself. Now, how do I get the slides? That seems to be it. Okay. That's what I wanted. Ah, that's not what I wanted.
Leave it like focus, you've got to zoom it. Yeah. That was what was wrong last week.
That's got it. Now this, I don't know whether we can reduce the slide here, but maybe we can manage. This is an actual spectrum. It's just printed from the photographic plate. Oh, thank you. Which shows just what I was indicating. that you have here the iron arc, and here's the spectrum of a star. This particular star is Arcturus. And in many cases, you can see that the lines in the arc have counterparts in the star spectrum, dark lines, and they're slightly offset. The dark lines in the star spectrum, they're offset a bit to the right, and that would enable one to measure the velocity of the star Arcturus with respect to the observer. Now that spectrum is on a very generous scale, and the sort of spectrum that one is normally confronted with is more like this. This is actually an original spectrogram, a complete one, that was taken at the Cassegrain focus of the Isaac Newton telescope when it was at Herstmonceux. And it's on a plate which is small enough that I've simply been able to stick it to a slide and project it. This is an original spectrogram that was exposed in the Isaac Newton telescope. And you can see it's exactly the same sort of thing. This is the star spectrum. It's a negative, so that the emission lines in the arc spectrum appear black, and the absorption lines in the star spectrum appear white. But it gives you more an idea of the scale. Now, if I could go back to the taking a picture of the spectrum was only the first part of the procedure. Once you've got it, and this is an enlargement of that small slide or part of it, you then had to measure it, and you measured it on a travelling microscope, where you look in a microscope and you have a wire which you have to move the spectrum about under the wire, and you bisect the lines in the star and the lines in the arc successively, and you make a note of what the readings are, and afterwards you have to do some arithmetic, and that's before the days when computers would help you, you see. So it was really quite a palaver in order to get the velocity. Well, the procedure that I developed, it was quite soon after I was a research student. It was too much of a task to try to undertake as a research student, and I should tell you at the outset that it wasn't my idea. The idea had been had by one Peter Felgett, who was employed at the observatory earlier than I was, and it was sort of floating around at the observatory during the time that I was a research student, but it was too much to think of trying to implement it then. But I tried to implement it afterwards, and the principle was to make use of a photomultiplier cell, and instead of receiving the spectrum on a photographic plate where you could see the whole spectrum and measure it line by line, you received it on a mask, or diaphragm as it was called in those days. And this diaphragm was designed so that it was like an opaque strip that would obstruct all the light, except that it had clear apertures in places that corresponded to absorption lines in the spectra of typical stars of the sort one hoped to observe. And you can see in a general sort of way that if it only transmitted the places where there were absorption lines, then if you had the mask accurately in register with the star spectrum, only dark lines would be transmitted through the apertures in the mask. Whereas in any other position, if you move the mask with respect to the spectrum, then bright parts of the spectrum will fall through gaps in the mask. And I've got what I hope is a fairly convincing demonstration of this here. That this picture is supposed to represent this star spectrum. It's a bit idealized in as much as it shows the absorption lines as completely black and the rest of the spectrum completely white. and this is the mask, or it is in fact a photographic print from mask that I actually made for the instrument, and you'll see where there are 3 lines here, there are 3 gaps in the mask. So if I show you now what the instrument actually did, I'll put it out of register sideways so that you can see what's happening. And you look here, you see that where there are gaps in the mask, largely light parts of the spectrum are falling through it. That would be the usual situation. And then I'll try to scan the mask along, and at one unique position, all the gaps in the mask are systematically filled by the corresponding absorption line. And so you get a rather sudden darkening because all the gaps are systematically filled by dark lines. And you can imagine that if you now collect up all the light that passes through the mask with a big field lens, and you focus it on one photomultiplier, and all you have to do is to move the mask along gradually, with a micrometer screw, and you look for a place where a minimum of light is transmitted, and then you know that the mask is accurately in register with the star spectrum. Then you return the telescope to a different star, where you get a spectrum which has a different shift because the star has a different velocity. You can again find where the mask is in register, and the difference in position gives you the difference in velocity between the 2 stars. In order to implement this, you need to have 1 or more stars of known and constant velocity. Well, I tried to implement this at the 36-inch telescope, and this is a cross-section of the system viewed from the west. There is the telescope, and then the light went up to the Coude focus, which is not attached to the telescope, so you can put equipment as big and heavy as you like there, and it doesn't have to be turned upside down as the telescope moves. And then there was this instrument, which was physically quite big, but it was basically a more or less conventional stellar spectrograph, whose focus was here, the spectrum was formed here, and there was the diaphragm and a field lens and a photomultiplier, and it had to have comparison channels as well, but that was just for technical reasons and weren't fundamental to the principle of the thing. Now could I go back to the slides? This shows a picture of the 36-inch dome that was taken from a hot air balloon or something, and a long time ago, when the Northumberland dome was black, as you can see, and some of the trees were not as tall as they are now. In particular, that you see the Wellingtonia is not as tall as the beech trees. This actually shows the business end of the spectrometer. It looks rather complicated, and inevitably in detail things get more complicated than the principle is. But the mask is at this level here, and the light that's transmitted through it, it goes into this large field lens here, which images it. Well, it actually images the primary mirror of the telescope on the photomultiplier, which is down here. This rather elegant plano-convex lens, it's an aspheric lens, and it was a very cheap lens to make. I haven't got a picture of it being made, but I did think when I subsequently made an analogous instrument for the 200-inch telescope on Palomar Mountain, and I made the lens in just the same way. I had the foresight to take its picture while I was doing it. This is a block of perspex, and it says something for the time that I put some objects, some everyday objects there for scale, and you see one of them was a slide rule, which was that was the computer of the day. This shows some nocturnal activity in the observatory's workshop, which took a great deal of clearing up to the point where nobody was supposed to see that any perspex swap had been made that night. And you could see that, in fact, I faced the flat side first of all, and then rather crudely bolted it to a face plate to do this curved side, which was made to an aspheric specification. And there is the finished lens. You can see the tapped holes by which it was held to the face plate, and then a slice was cut out of it because it was only a narrow slice that had to go by the spectrum. I got the workshop to cut a slice out of it. And I've got the remnants of it here, and you can play with it afterwards and convince yourself that although it's made of perspex by a very crude procedure, it does work quite well. I mean, it's only intended to be a field lens.
Did you turn it by hand to get the asphericity, or did you make some sort of mask for it to follow?
No, I calculated it by a fearfully crude method, what it was supposed to be like, in radial steps of a 16th of an inch. So it had, and then I made it with looking at the dimensions on the lathe, advancing the tool by the proper amount, so then I finished up with a lens that had steps of a 16th of an inch on it, and then while I spun it as fast as possible, I held sharp edge and graving tool effectively against it until I just got to the bottom of all the steps, and then I went through very much the same process as optical grinding. I used glass paper in successively finer grades, merely cut in my hand on the curved surface of it, and finally polished it with brasso on cotton wool, which brings up a polish in just a minute or so. A very effective way of getting a polish on perspex. And it really makes quite a nice lens, and ever so cheaply. I think it didn't cost any more than just a block of perspex to start with.
You put a new picture on cutting face of technology, doesn't it?
Well, this shows me as a youth with the upstairs part of the instrument, and you'll see this is the chair of observational astronomy, to which I've only actually just been appointed. And this is where you set the telescope. This is the eyepiece from which you see the view. You see, you don't have to get up from the chair to do any of this. So you set the telescope from here, and you see the view. And these were electrical controls for the spectrometer. And then there's the Brown recorder chart. The output didn't come on a computer, because the computer was hardly invented then. But it came on a strip chart, which emerged from this Brown recorder at a rate of an inch a minute. And here is such an original chart which represents a night's work on the 36-inch. You could have used yourself looking at the same time as this lens afterwards. And this shows what the output looks like. You have to imagine that time is increasing in that direction, and the chart moves an inch, which is about this much in the picture, per minute. And what happens is you start scanning the mask, and nothing much happens to the brightness for a time, and then there's an abrupt minimum. This is the minimum as we go through the position of register. Meanwhile, the instrument itself is putting on these marks, which served as fiducial marks. They were just put on by the gearing system as one went through the scan, by short-circuiting the signal momentarily. in a moment it came back again and it resumed where it was going. And then when one had seen this dip, as I called it, nothing else was going to happen however far one scanned, but then I switched a switch which reversed the direction of scan and went back through it again and went through it several times. And then at the end I went quite a long way beyond here, ready for the next star. And the next star, you see, it comes in a completely different place on in the scan. We've gone all this distance, and each of these marks is some 10 or 12 kilometers a second apart, and we've come to a star with a very different velocity next. And so that was how that instrument worked. The chart had to be read afterwards, and I had this to read it with, which is just a rectangular perspex sheet with a scratch ruled on it with the corner of a screwdriver. And it's instead of the very elegant travelling microscope that costs £10,000 that you use photographically, you have this square of perspex with a scratch ruled with a screwdriver, and it had to be laid on the chart so as to bisect each of these dips in turn, and the position read off against the fiducial fence of marks there. Well, when I was trying to develop this procedure, I think we can leave that on there and put this on top. At that time, there had been, comparatively recently then, this was in the mid-60s, there had been a general catalogue of radio velocities. 15,000 stars were known, but only 1,500 had velocities that were good to 1 kilometre per second, and they were nearly all stars brighter than magnitude 5.5 that had been observed at the Lick Observatory. Now, my boss, who was the professor of astrophysics and had been my PhD supervisor, Redman, he had his own experience of measuring radio velocities, and he'd used the Dominion Astrophysical Observatory's 72-inch telescope. And he had a program on 7th magnitude K-type stars, and they took 2 hours exposure to get the spectrum, and they gave an accuracy of about 6 kilometers a second standard deviation. And in order to sort of get clear with him what it was I was trying to do and what sort of result I was hoping to get, I told him that what I thought we'd be able to do with the 36-inch telescope was to measure 59th magnitude stars in a night to 3 kilometers a second. So we got a telescope with only a quarter of the collecting area, and instead of doing maybe 4 stars in a night, I was offering 50. And they're 2 magnitudes, that's a factor of 6 fainter, and getting twice the precision. Well, when I suggested that, Redman was quite taken aback. Now, Redman was a naturally pessimistic man, or so it was thought. He was really realism, I have to say, but he had a great reputation for pessimism, and he certainly wasn't one for celebrating unnecessarily, but he said, ha 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 ha, he said when I suggested this, and he said, if you ever manage to do that, he said, I will stand a magnum of champagne in celebration. I apologise for looking so old and frazzled now as I speak to you, but I was less than half my present age then, and that is Professor Redman, and that is his magnum of champagne. It was only about 18 months after he laughed at me that I was able to connect. I've only got one more slide which I may as well show you now. I'm afraid I scrapped the old instrument with its brown recorder, and Dr. Mentfer here and Mr. Schneider, between them, they've managed to make this instrument go, which is it's quite a small and compact instrument, and it's working at the 36-inch telescope here, but not at quite the same focus as the other one. and the observing station is now here with the same eyepiece, the same 19th century eyepiece to find the stars, and it works through a computer and it does the reductions itself. So now I've finished with the pictures. I've also finished with my explanation of radio velocities. I'll stop making jokes against myself and tell you about Zeta Cancri. Now, first of all, I may tell you that I should say that I was pessimistic in thinking that I'd get 3 kilometers a second accuracy. I actually got 1 kilometer per second from this instrument, so that was another factor of, as it were, 9 in terms of information density. But the instrument actually gave a higher accuracy than I had dared to hope. Now, this is a picture of the multiple star Zeta Cancri as published by Flammarion in 1878. It doesn't look anything like this at all in a telescope, because this whole field that he has drawn is actually about 12 seconds of arc across. And so this is how it would look if you looked at it with the space telescope with an eyepiece of very high power. A and B here, they look like one star if you're not very careful, but this other component is about 6 seconds of arc away, the star called C, and that I think it was first noticed by Flamsteed in 1680. Sir William Herschel, looking at Zeta Cancri in 1781, first saw that the primary star was actually a close double itself. These stars are hardly 1 second of arc apart. Probably using the same telescope as the one with which he discovered Uranus, and at a date quite close to that. Herschel noted in his observing book, "If I do not see extremely ill this morning, 4 a.m., the large star consists of 2. And of course that is actually the case. It's a triple system. And A and B, they circulate about one another in a period of about 60 years. C being much further away, it moves much more slowly, and it probably has a period of the order of 1,000 years. Now I can show you an orbit that was, it's in the sort of computed orbit, but a diagram of micrometer observations which show the position of B with respect to A, the brighter component. This is the close pair of stars, and this starts in 1826, and the measurements go round more than one cycle to the time when this diagram was published in the early 20th century. And it shows the sort of accuracy with which you could get an orbit of a star of this sort. But although the close pair was a fairly straightforward one to observe, except that between the first observation and the second one, it made about 3/4 of a revolution. And when it was observed again, it was found to have gone from, as it were, here to here. And then the next observations, they came here, and it looked as if it had reversed direction. But pretty soon people tumbled to it that really it had gone nearly the whole revolution between the first observation and the second. But the more distant star, the star's called C, Zeta Cancri C, it started to create trouble because Sir John Herschel in 1831, this is where the 170 years comes in, Sir John Herschel in 1831 complained that it didn't move in a systematic fashion, that it appeared to be going at one rate and then the rate changed. And he said, "It appears to me on the whole likely that mistakes have been committed which it is now impossible to rectify or allow for." Well, now the next person who took a great interest in it was Wilhelm Struve, the first man of the great Struve dynasty of astronomers. And he was rather fortunate because in 1824 he took delivery at Dorpat of the famous Fraunhofer refractor, which was a 9.5-inch telescope, which was it was the largest telescope of the day. And furthermore, it was on an equatorial mounting. Now Herschel's telescopes had been on alt-azimuth mountings, so it was very difficult even to keep a star in view or to find it in the first place if you were using the high magnifying power that you needed in order to measure the position angles and angular separations of stars. The equatorial mounting was very much easier because you only had to move it in one coordinate to keep the star in view. And the Fraunhofer refractor was the first one that had a clock drive on it, and so Struve had a much better chance of making accurate measurements than anybody else. And he brought out, first of all, a new catalogue of double stars, which was, he liked Latin, so it was called Catalogus Novus. And it had rather more than 3,000 double stars, of which about 3/4 were his own discoveries, mostly made with this new telescope. And then, after a lapse of about 10 further years, when he'd observed all these stars repeatedly, he brought out an enormous volume called the Menciae Micrometricae, which is not only a formidable work in terms of the observations that went into it, whose accuracy, I may say, bears comparison with any that have been made since by visual methods. But it also has an equally formidable 200-page introduction, all in Latin. It makes it rather difficult if you want to learn anything about how he did it. Anyhow, about the time that he wrote the Menciae Micrometricae in 1837, he was instructed by the Tsar Nicholas to leave Dorpat and go to Polkovo, which is on the outskirts of St. Petersburg, to set up to the Polkovo Observatory, which was a more grandiose observatory than any that had gone before, and it was furnished with a 15-inch refractor, which broke the record for aperture by Merz and Mahler, who were the people who succeeded Fraunhofer. Fraunhofer only lived to the age of, I think it was 39. But Merz and Mahler were his successors. So he had this fine new telescope. The only thing is he didn't have time to use it because he was so busy, first of all, getting the observatory up and then directing it and administering it. But he had the foresight to produce in the person of his son Otto an observer to take over from him. And so Otto Struve started in 1840 to make systematic observations with a new telescope at Polkovo. And he observed Zeta Cancri particularly carefully. And in 1874, when he'd been observing it 34 years, he brought out a paper on it, which is of particular interest in connection with this star. It was in the Compte Rendu, in the French Academy's journal. And in it, he gave the observations that he and his father had made. They'd been made in 39 out of the previous 46 seasons. He didn't bother with anybody else's observations. They were just the Struve observations. And he showed that the distant component C, it appeared to move about 10 degrees of arc in 10 years, and then it seemed to stop for about 10 years, and then it would go on and move some more. And Struve conjectured that what was wrong with C was that it must be in a small private orbit with what he called an opaque companion, that's to say a dark companion that you couldn't see. And in that, in fact, he was exactly right. That is what it has, and it's the explanation for its apparently jerky motion. Well, then there was a great scandal erupted in 1878, which was 4 years later, when Flammarion accused Struve directly of plagiarism in a catalogue that Flammarion brought out. And Flammarion was a very sort of popular and influential French astronomer, although he was also something of an amateur. Had a lot of trouble with his employment. Flammarion said that it was he who had drawn attention to the jerky motion of the star seed, and that Struve had merely copied him. But he had written to Struve in 1873, the year before Struve's paper, asking for his observations of Zeta Cancri, and Struve hadn't sent them, and instead he'd submitted a paper to the Comte Rendu. Flammarion was particularly incensed that he would send it to the Comte Rendu in Paris, which was just where Flammarion lived. But actually, Struve, I think, was quite innocent in this matter, because he sent papers on various subjects to the Comte Rendu before, and he had more right than Flammarion did to send papers there, because he was what amounted to a foreign associate of the French Academy, whereas Flammarion never had membership in the French Academy at all. But Flammarion insisted that before Struve's paper had been published, though after it had been received by the French Academy, he had deposited with the French Academy a pli cachete, that's a sealed envelope. Now the Academy had a great procedure for accepting sealed envelopes, and that had started in the early 18th century. And I think it was really intended so that people who were claiming inventions could assure their priority without at the same time publishing the invention until they got patent protection on it. And the rules were that the person who submitted a pli cachete, he could withdraw it at any time. But after he was dead, it could not be withdrawn, but his heirs could require it to be opened. And after 100 years, the Academy itself could open it at its own discretion, and it could then either throw it away or publish it or do what it thought with it. And Flammarion challenged Struve to have his pli cachete opened. Well, Struve didn't take any notice. And you would think that it would have been a matter of some interest to know, even at that time, what the score was on this issue, because if what Flammarion said was quite untrue, you think that it was sufficiently libelous that Struve would do something. And on the other hand, if it was true, you'd think that Struve's reputation would be thoroughly sullied, and in any case, Flammarion would be only too keen to have his pli cachete officially opened and its contents disclosed. But that didn't happen. But with great difficulty, I discovered that in 1989, the pli cachete had been opened, and this has happened because the Academy had decided that it must do something with all these pli cachete that it accumulated. It had about 16,000 of them in stock, and it appointed a commission which met initially 3 times a year and opened about 100 of them at a time. It did this in 1976 and tried to see what they all said and to do something sensible with them. And so it came about that in 1989 the Commission got round to opening Flammarion's pli cachete, and it sent it first of all to Coquer, who was a distinguished French astronomer, who in turn sent it to Couteau, who was a double star expert. And Couteau actually published verbatim, I think facsimile, in a publication which nobody here had ever heard of. A facsimile of, it only consisted of 3 pages, and I managed to get from the French Academy photographic copies which it was possible to read. This is the first page, and you see it's just in Flammarion's handwriting. There's another page that looks much the same, and then there's a diagram. and this diagram, even in the photographic copy, it's right at or in places beyond the possibility of reading it. And in trying to write this matter up, I read through the diagram myself to the extent that I can read it and translate it into English while I was about it. But what it shows is what you see there. Flammarion had taken component A as being the centre, and then he'd drawn where component B appeared to go, which was in an ellipse around it, which was all right. He'd also drawn a small circle which was supposed to be the path of the centre of gravity of A and B. Basically, it's just halfway between A and B, more or less equal stars. So fortunately, it doesn't make a lot of difference whether you're considering the centre of light or the centre of mass. And then C, he'd shown doing this, which is a sort of epicycle, but actually, when you come to look at it, it more or less follows B. And the reason for that is that instead of taking the midpoint between A and B as being the sort of centre of the system, Flammarion had always measured from A. And this was quite misleading. It only shows one of these sort of epicycles in the whole interval of 50 years for which there were continuous observations. And that's actually not what it was doing. Well, although Struve didn't he didn't try to determine quantitatively what the orbits were. He simply said C must be in orbit around a dark companion. The problem was taken up by Seeliger, who was a distinguished German astronomer with no small computing ability too, it seems, in 1881, and again with a still more magisterial treatise in 1887 or 1888. And the actual path of the star, these are annual mean positions that you see here in this rather jerky line. And this is Seeliger's ephemeris from the computations that he made about the orbit. And you'll see it fits extremely well. And you might think that there could be no doubt that really was the answer to the problem. However, Burnham then entered the fray. Now, Burnham was an astronomer who was extremely good at measuring double stars. And he used the lit telescopes, first of all just the 12-inch, and then he graduated to the 36-inch. And he could discover, never mind measure, the most difficult double stars. It is quite incredible what he managed to do. But he wasn't one for believing in things that he didn't believe in. And he tried to publish a refutation of Seeliger's work. And he shows here, it sort of opened out. He's plotting separation against position angle, and it comes down here. And this is Seeliger's ephemeris. Unfortunately, he didn't plot it at quite the same scale, so it looks as if these things are slightly too close together. But you see, it fits extremely well. The ephemeris shows, just as it does in Seeliger's own picture, that is what it's doing. But Burnham insisted that you could take any star which had more or less the same angular rate and separation and plot its annual means in the same way, and they would be bunched in much the same way. And he gave examples here which I don't think are very compelling. And there are some more. Now this one is rather compelling. And the exciting thing about this one is that in this one he actually discovered that this was a triple system just like Zeta Cancri. And this bunching was indeed caused by the motion of a close pair. So it was exactly analogous to Zeta Cancri. And the amusing thing is that Burnham himself had discovered the close companion to this system, but he insisted that it couldn't have any possible effect on the measurements of position, angle, and separation that he was making. But the fundamental thing that he'd overlooked was he was only concerned with the measurement. And it was true that because the close companion to the bright star, it was faint, it didn't interfere with his ability to set his micrometer wire on the primary star. But what he didn't realize was that although the stars were so disparate in brightness, they had really quite similar mass. And so the primary star itself was in an orbit whose size was something like half the separation of its close companion. And that was falsifying the measurements of the distant component. And so Burnham was really barking up a gum tree with this. Well, naturally, Seeliger was not very pleased to be told he was wrong, especially when he wasn't. And so he published a complaint about Burnham's work in Astronomy and Astrophysics, which was a German journal, not the same as the present Astronomy and Astrophysics, but it was one that had a rather short lifetime in the 1890s. He said that Burnham must have read his papers either very superficially or not at all. Well, Burnham was displeased at that, so Burnham had another go in Astronomy and Astrophysics, and rather unwisely, he didn't confine his strictures to Seeliger's analysis, but also assaulted his person in his new paper. And Seeliger responded in a rather dignified fashion to that. First of all in Astronomische Nachrichten, and then to Burnham's credit, he had a translation of it published in Astronomy and Astrophysics. And I don't know who did the translation into English, but it was someone with an absolutely wonderful command of English, and it may have been Seeliger himself. I wouldn't be surprised if it was. But in the English version of the article, Seeliger said that Burnham's ad hominem criticisms were in a tone which I must most decidedly qualify as entirely improper. And then he pointed out that the departures from uniformity of the motion of C had begun on their fourth repetition now, and he accurately paraphrased Burnham's assertions as saying that they were merely a remarkable accumulation of personal errors now occurring in the same order for the fourth time, and said that to criticize the like assertions with a parliamentary expression is scarcely possible. Well, not much more could be done because a sort of immovable, irresistible force had met an immovable obstacle, and so a sort of truce was called. But I go on now to 1936, when Bayes, who was a great French double-star observer, he actually plotted the positions. These are the annual positions of Zeta Cancri C up to about the time that he was publishing this picture. And you can see clearly how it goes in this set of apparent epicycles. And 40 years later, it had been observed photographically. Sufficiently wide separation that it could be measured photographically and much more accurately. And these are the photographic observations, which you see they fall much nearer to a smooth curve. This is in angular separation, and this one is in position angle, and you see exactly the same thing again. Well, I now come at the 11th hour to the radio velocity business. It was about the time that Bayes published that second picture that I started radio velocities of the object, and I mean, ever since about 1900 it would have been possible to make the radio velocity measurements over the period, which is about 17 years, of the small orbit of C, in order to see whether radio velocities actually verified the idea that C was in orbit about the dark companion. But nobody had actually done it, so I did it. And these are my observations. The open circles, which are the majority, there are 69 of them. They represent observations with the original spectrometer with its ground recorder output. And the filled circles, they were made with the more up-to-date instrument at the Haute-Provence Observatory in the south of France, near Marseille. I may say that on one occasion in 1994, I actually called on Bayes at his home in France in the course of travelling on my bicycle between Cambridge and Haute-Provence. And I spoke to him about Zeta Cancri and obtained his permission in writing a paper about it, which I didn't do for several years later, to incorporate his diagram of 1936. So he gave permission for it to be published republished nearly 60 years after he first published it. So you see, I got this orbit, and if one compares it with what would be expected on the basis of the calculations by Seeliger and subsequent people, it fits quite extraordinarily well. Gastayer was about 1950. He was probably the first person to be able to tell what the expected masses of the various stars in the system were. This is all done from absolute astrometry. Not only the relative positions of A, B and C, but also the actual positions in the sky. That made it possible to tell what the relative masses were of the AB system and the CD, if you call it that, system. And the only thing which is added to this picture from radio velocities is this scale of ordinates. The actual numbers on the scale, the amplitude of the velocity variation, and the shape and facing of the orbit, they come entirely from the micrometer measurements and the astrometric measurements of the star. And this was an orbit that was published by Heinz in 1996, really quite recently. And you see, they fit pretty well. Now, Seeliger had no way of knowing the masses, and so in order to show where his theoretical radio velocity curve comes, I've had to adopt an amplitude, that's to say the vertical scale, as well as the vertical position. And it fits extremely well, except for this change in phase. You see, there's that phase offset. And all that is due to is that the period, Seeliger's period, was slightly off, and there's a difference in epoch of 130 years between the observations that Seeliger was using and the ones that I was using. And because he got the period about 2% in error, the orbit has gone considerably out of phase. If you correct Seeliger's period by about 2%, you get that, which fits so absolutely perfectly, I mean practically as well as it's possible to fit it at all, that I hesitated to show that one without that, because it looks as if that one, it must be a swindle that it could fit as well as that. But the fact was that the orbit that Seeliger derived was, for all practical purposes, perfect. Well, having shown then that the radio velocities confirm absolutely the astrometric orbit, the thing that was left to do was to wonder what the nature of this opaque body was, because the observations showed that the CD system had about the same mass as the AB system. A, B and C are all stars very much like the Sun, and the fourth star also had a mass that was similar to solar mass, and very difficult to know what it would be. Well, white dwarfs can have that sort of mass, and they're very faint. But white dwarfs, they should have been discovered by the International Ultraviolet Explorer in a relatively nearby star like Zeta Cancri. And the other possibility, which is the one that I always thought was the correct one, is that the unseen object must itself be a binary star, because two stars of half a solar mass, sequence stars, they can be very faint, because the luminosities of stars, they vary by leaps and bounds with the mass. So by the time you go down to half the mass, stars are quite faint, 11th or 12th magnitude compared with the 6th magnitude of the other stars in the system. And so I thought that, especially if one looks in the infrared, where a cool star would be relatively brighter, with one of these modern adaptive optics systems on the large telescope, it would only take a 1 second exposure and you could see this star which had caused all this trouble for 170 years. But could I get anybody to do it? People merely ignored me or refused. Finally, I gave a talk analogous to this one, if not slightly more high down, at the Institute of Astronomy a year or so ago. And there was in the audience, quite by chance, there was a man from the Dominion Astrophysical Observatory who came to me afterwards and said, well, he had colleagues that were on the CFHT, the Canada-France-Hawaii telescope, a 3.5 meter telescope in Hawaii, and they had adaptive optics on it, and they were on it right now, and he would email them and ask them to look at it tonight. And he did so, and they did so. And this is what they saw. This is a, there's A, that's B, and that's C, and there is D, there's the star that had never been seen. You see, very much fainter. That's at 1.2 microns wavelength. That's at 1.7 microns, where you see D is now much brighter with respect to C, and at 2.2 microns it's getting on for the same brightness. That's an enlargement of one of these pictures. Of that one. It's an enlargement of that one. You'll see incidentally how the resolution of the telescope decreases as you go towards longer wavelength, and these are actually the diffraction rings around the airy disk. You see the first diffraction ring gets bigger too. So I think it's safely established now that the previously unseen star is in fact a pair of M-type dwarf stars, and there is an even more challenging trouble now, because of course one would like to see them separately, which is either going to take further increase in the resolution or spectroscopy of this object to show that it's got two spectra, it's double lined, and which will be the less difficult depends on what the period of that star is. We could have a period anything from the order of a day to the order of a year. If it's the order of a year, then it would be nearly resolved in this picture. If it's of the order of a day, it'd be very difficult to resolve in angular terms, but its velocity amplitude would be very large, and so it might be more practical to see it spectroscopically. But that's a challenge which is left for the future. But otherwise, the situation concerning Zeta Cancri is reasonably satisfactory. Thank you very much.
Are there any questions?
The spectroscopy would have to be in the infrared.
Well, I think so, because it's otherwise so difficult to see the thing at all. Liable to be swamped by the nearby star C. The difficulty has always been that it's been so faint. You see, it's about 4/10 of a second of arc apart. and speckle interferometry, ever since it was invented, easily do that. But it's never been possible to resolve it because the disparity in brightness at visual wavelengths is 5 or 6 magnitudes. So it's a factor of 100 or more. And there isn't a dynamic range in speckle interferometry really to see that. And further to resolve it and get spectra of it would be, well, it would be a difficult task. The Space Telescope might be able to do it, because the Space Telescope doesn't have such trouble from the spreading of light from one object to another.
Then there are new satellites to be launched, which is specially designed to look at stars in the infrared. I don't remember what its name is, that's the trouble. It's about to be launched.
Yes, well, there are various pretty powerful instruments that are in orbit. I don't think that there's anything that could do that. No. The Space Telescope might do, and its successor would be able to, I feel sure.
That would be looking at it from the reservoir.
It would be looking at it, well, yes, it would be as far to the red as it could reasonably go, I think.
Are there any other star systems like this?
Other systems like
Other
this?
systems, yeah.
Yes, there are actually. The people with the CFHT, they got quite excited about doing this so easily when it was pointed out to them, and they wanted to know what others they should play with. And there is in fact one other that I was only able to think of one that was analogous, and that is Zeta Cancri, which is it's a visual double star system. The visual components are between 1 and 2 seconds of arc apart, and each of the stars is itself a spectroscopic binary. And there was reason to think that it might be possible to resolve one of them has a period of only 4 days, and it will be too close in angular terms. But the other has a period of a year and a bit. The visual system has quite a long period. I don't remember now what it is, but it's of the order of a century. And the star which has a period of a year and a bit, in principle, could be resolved by the CFHT system, and in fact it was resolved. What they're doing now is observing it for a year and a bit until they've got observations around the orbit. It already has a spectroscopic orbit for that star, which I did myself.
What happened to the original Corabel?
The original Corabel. Corabel is the name of the one that I, as it were, scrapped.
Well, yes, I must admit I was trying to feed you the question. I thought there was something interesting about it.
Well, that instrument, it was in service for 25 years, from 1966 to 1991. And I only got rid of it then because supposedly I was getting a new instrument, but there was a bad story about that. It was only the questioner and his colleague John Schneider who managed to retrieve the situation for me, for which I'm profoundly grateful, I may tell you. But for several years I didn't have an instrument at all, and that was through banking on having the new instrument as soon as the old one was decommissioned. When I say decommissioned, most of it actually went into a skip. Well, I know it does seem a bit rash, but you see, it was physically a pretty large instrument. It was a kind of Y shape, and it had arms that were the order of 10 feet long. And mostly it was just a conventional spectrograph. It was only the part around the focus which had the mask and lens and so on in, that was the novel part of it. And when I took it to pieces, it was rather pathetic what was left. There were some steel tubes that had been welded up out of steel plate, and a selection of old bits of string and sealing wax and things. But Nothing very much, apart from this, the end that I showed in the picture that has the lens in it. And what actually happened was that part of it went to the Science Museum as a historic instrument. So it's there supposedly, it's supposedly permanently preserved. It's not on exhibition because McDonald's or somebody got a display of groceries at the place where the astronomy part of the Science Museum used to be. But it's in store at Olympia, and I suppose one day when astronomy is thought more important than groceries, it'll be excavated, and then it might be on exhibition.
We did have a 9-inch diffraction grating.
It was a 6 by 8 inch diffraction grating. Yeah. Well, we put that back in store. But,
that's delightful objects.
Well, yes. It actually did look a bit worse for wear actually being in this instrument, because although I tried to keep the interior of the instrument desiccated, it was by no means airtight, and there was a place just near the diffraction grating where damp air routinely got into it, and it hadn't improved the appearance of the grating. There was also a collimator mirror and a doublet lens which served as the camera. The lens was okay. The mirror was a very good mirror. Redmond wanted me to get it from Club Parsons. I actually designed and had this spectrograph constructed in the observatory's workshop when I was a research student, although I didn't use it for these experiments for radio velocities then. And Redmond thought that the mirror should be obtained from Club Parsons, who would have been charged, even in those days, maybe £200 for this mirror. It was just a 6-inch collimator mirror and nominally a paraboloid, but there's no difference between a paraboloid and a sphere at the focal ratio that it had to be, which was f18. And being much in touch with the amateur community then, I said, well, Henry Wilde would make a mirror like that much more cheaply. And Redmond seemed rather doubtful about it. I asked Wilde for a quotation, and he quoted £10. Well, Redmond could hardly say we couldn't afford £10, you see. And I assured him that Wilde was a good mirror maker and had a good reputation in the amateur trade. So Redmond let me order the mirror from Wilde. On the 5th day from the day the order was sent out, the mirror arrived by parcel post, already illuminized and everything. And Redmond couldn't believe it. Redmond gave it to Linfoot, who was the assistant director and the optical expert, to test. And Linfoot did a Ronchi test on it, and the fringes, they were perfectly straight. Linfoot had to tell him, this mirror is, as far as I can tell, perfect. And Redmond said, well, I guess it's not the right focal length. So it was a 6-inch f18 mirror. It should be 108 inches focus. It should be 216 inches radius of curvature. So Linfoot was sent back to measure the radius of curvature. And as accurately as his tape measure would measure it from his Ronchi test, it was 216.0 inches. So Redmond had to admit that evidently Wilde could do the job. And so that is the mirror that was always in that instrument. And well, it still exists. It's a very nice mirror.
Could you actually make a telescope out of it?
Well, an f18 telescope, it would be a bit unreal.